Okay, everyone. So welcome to lecture 27 of ECE 3311, Principles of Communication Systems. So today's lecture is actually very important, as sort of the next level of doing anything with a communication system, which is regarding, first of all, ooh, I forgot the most important thing, my video. Okay. Yeah, because I'm wondering, I'm like saying, why am I not showing up? Okay, now I'm showing up. So no, very important. This lecture is about being able to find out what is the loss incurred by a communication channel. And I mean communication channel from transmitter to receiver, including things like the radio frequency front end of that system, right? So what the heck do I mean? So let's back up. Okay. So when we talk about a communication system, right? So let's just move this guy away here. All right. So we so far what we've been talking about is we have the source, right? And then afterwards, that source, let's say we assume it's binary. Okay, so binary, right? Then we do the mapping, right? The modulation. So now we're talking about symbols. Okay, great. And then what happens is we do the up conversion, convert, right? So now what we got binary, symbols, up conversion. So symbols, let me think. Yeah. Symbols. So this is the baseband. Now we have the signal, and that's at passband. Okay, and then what it does, okay, is that it goes through radio frequency front end. Okay, so what exactly happens there? In fact, what happens is, depending on how you implement this, well, how would a transmitter look? Okay, so let's redo this because I'm not satisfied. We should work backwards. Okay, so at transmitter. I'm going to miss a lot of stuff, so please bear with me. I'm not going to include everything, right? Okay, so we have the antenna. See, even that. Okay, so that's antenna. Again, this is a wireless example. Let me think. There could be a number of things, there could be in this stage. Okay. You're going to have things like, for instance, analog filters. Okay. We could have like mixers. We can have local. We have amplifiers. My favorite, the power amplifier. Amplifiers. Okay. And a bunch of other radio frequency front end components, right? Okay. One of the big important things, remember this passband modulation, right, is the mixing. Okay, the mixer. And this enables us to go, this thing obviously is connected to some sort of local oscillator. Again, super idealized. It's actually more complicated than that. And that provides us with if that's at FC or some sort of F, and then our FC, our carrier frequency is built off of that. That's where, your cosine and sine is all built off of, right? Then, of course, you have, your digital to analog converter. Okay, and then you have things like your modulation, to a specific symbol, right? Here's your binary source. Now, again, super idealized. In fact, before the binary source, probably going to source and channel encode. So let's say channel encode. You're probably going to source encode. And you're going to have your binary source, right? So yeah, so like for instance, yeah, so let's say for instance, you do the mixing. Okay, great. So you mix your signal up. Perhaps you also want to filter out any sort of harmonics. Perhaps you want to amplify your signal. So it's at a specific, like imagine here, it's at a specific power level, but you want to crank this thing up, right? So yeah, so like for instance, like I'm gonna take a stab at this. Okay, so suppose you have something like this. So you have the mixing. Let's say you have some sort of bandpass filter. Then you have a power amplifier, PA. And then that's what gets, so things like, you know, this removes unwanted harmonics and other stuff. You just want the signal to come out of your transmitter and make it obey, let's say, any sort of spectrum regulations. Unwanted signals. Okay, let me, unwanted components. Okay, and this is your power amplifier. So this is a band pass filter. This is your power amplifier. Again, super idealized, right? So this is an example, but something fits in that box, right? And we also saw what happened with the super heterodyne transceiver design, about how we can upconvert multiple stages, you know, multi-stage, and then also the same down. So this, again, super idealized. But very importantly, what happens is at every stage, okay, after you digitize and such, there, you know, like your signal is now an analog signal. And every component either contributes a gain or contributes a loss against the signal with respect to its amplitude, respect to its power, right? And so we need to account for that, right? Because we, like right now, if let's say we have, this is at the transmitter, and suppose now I draw out a receiver. And again, my apologies if this looks like super, like, wow, what the heck is Wyglinski doing? Like, my apologies, okay? It's I'm going to get to the punchline in a second, right? So you receive the signal. This we exactly saw, okay, several class tests ago. So you bandpass filter out the desired signal band, right, BPF. We amplify it because it's probably pretty weak. That, the pretty weak part is what I'm getting to, okay? So we amplify it. Well, down convert it. And again, superhead with multiple stages, we could be having multiple of these. That's exactly, I think that was class test 4 or class test 5 where we did this, right? Then what happens is we might want a low pass filter out another component, right? So LPF, digitize it, right? To analog to digital convert it. Do the demod. We might also want to do equalization. Equalizer. Okay. Shucks. Yeah, so we try and extract out any sort of imperfections introduced by the channel. Right? Remember, this is receiver. So equalize, demod. Okay. We might want to, not a good place for that. So demod. This is a channel, so this could be some sort of decoder, a channel decoder, so it could be like Viterbi. Again, this is outside the scope of the course, but that basically what happens is that like uses the error correction codes introduced at the transmitter in order to smooth out any errors that might have been injected into the transmission and the channel. Source decoding. outside the scope of this course, and then the sink. Okay, so what I'm interested in, going back to the transmitter receiver, is this boundary. Okay. So what I'm interested in is, I'm going to use a different box, this. The analog stuff. Oh, and don't forget the channel. Don't forget that channel. So that channel, what color did I use? I used red? Yeah, I used red. Channel. At channel. So from TX, what happens? Well, so first of all, the channel, there's probably, and we saw this, there's some sort of propagation effects. Okay, like e.g. Okay. We also saw, like, even before that, what happens is, and I'll explain in a second, there's also, I call it a gain, but it's not a gain, it's a loss. Right? There's a gain, which is due to the physics, right, of transmitting a signal from one point, so free space propagation, right, or even just like propagating through a medium. What happens is your signal strength decreases, right? So we call this path loss. I'll explain that in a second in this lecture. So you have path loss. It goes through a channel. It gets distorted all over the place. We introduce noise, and it gets received by the transmitter, right? So, and this is totally in the analog domain. Okay, so this is really not rehearsed, but what I want to point out is several things. So several very critical things. So in this implementation I just like drew here, in this lecture and in the next, what I want to do is I want to point out sort of several key components that have very significant influence. If we have a transmit power at the transmitter, hence the transmit power, right? But if, let's say, like the thing is, when we digitize something, so a digital signal is very easy, right? It's like, what voltage level do you want? And you program it in binary ones and zeros. Even the signal constellation points at the transmitter, we can dictate what those signal constellation points are, right, in the I and Q domain, right, or the magnitude and phase domain. But once we analog digitally convert it, now it's really kind of like, it could be a continuum of values and components, right? The physics of a lot of different things begin to influence what that transmit power looks like once it comes out of the analog part of the digital analog converter. Specifically, things like the power amplifier. The antenna actually surprisingly plays an influencing role. Okay. This fella here, there was another amplifier in the chain, the receive antenna, okay? And then, so those two, and then things like, for instance, the path loss, 100%, 150%, the path loss plays a humongous role, end to end, right? And the propagation and effects and the like, okay, that's fine, that's fine. But let's simplify this if that is possible. Let's simplify this even further. So at the transmitter, right? So the power amplifier okay, and the antenna influence what the power level is at the output of literally my radio, my communication device, my transmitting communication device. In the channel, you got the path loss, right? So this path loss, okay, at channel. And then at the receiver, you have the antenna again. Boop, boop, boop. Antenna. And any sort of amplification here too, amplifier, okay? And there's more, there is way more, but this is like super duper simplification. So like you might say, okay, let's pick this apart. Okay, there are several things going on here, right? So actually, let's dig into the lecture. But the bottom line is, if I say, okay, I have a communication system, right? So it's one thing that if I have a comm system and I know what the baseline transmit power is, I ultimately want to know, right? So like if I know power PTX is, okay, I want to know what the receive power PRX is. Okay. Very, very important, because what does that do? Why is this important? Because of decoding, right? Or demodulation. Because remember, what happens is we have signals in there, we're down converting, we're digitizing, and we're putting it into some sort of equalizer. So we're correcting for all that imperfection. But then, oh, okay, now what's going on? And because think about it, signal to noise ratio. What are we like, signal power over noise power? We are very, very keen to know what the heck we are listening to, right? And if the signal's so weak, right, that's the part I'm worried about. If the signal's so weak, we need to figure that out, right? The signal's so weak. And why is it? Because factors like, what is the receive power? And it doesn't matter if we're blasting away. Well, it kind of does. Like, we know if we have the transmit power, there's a lot of physics that's in play that's affecting how strong that signal is at the receiver. It's not equal. Well, unless you crank it up, you have like amazing amplification hardware, but that has other consequences later on, right? So like, for instance, what are some of the factors? Well, several things. If we look at all of these, so obviously, like end-to-end power amplification, and just amplification in general, is going to have a gain. When I say gain, it really means gain or loss, right? It just means that I am either increasing or decreasing, because gain could be also in a linear domain multiplying against 0.5 or 0.05, right? It doesn't have to be always positive gain. It could be negative gain, right? In dB, that's going to translate into fractions, like a value below 1. Below 0, so minus 20, minus 30 dB, right? Usually we reflect everything in terms of dB, but there is a gain due to amplification. Antennas, surprisingly, have a gain. We usually measure those off of measure those gains off of things like, for instance, an isotropic antenna. And I'll explain what the heck that means. But there's a gain there, right? Different antennas have different gains. And very super duper, 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 duper importantly, the space, right? Path loss, okay, is literally the space, okay, the medium between TX and RX antennas. Very super duper important, okay? Okay. So equations to pay attention to, okay? Important, like this should be your cheat sheet for a lot of things. Important equations. All right, so first of all, the one that you're going to see a lot, this, obviously. So this one, speed of light, always remember speed of light. I know there's a lot of different constants out there. This is the only one I remember. I don't remember Boltzmann's constant and all those other things. This one I always remember. This is important. This is the speed of light. So what happens is this relates speed of light, and it's equal to the product of the frequency in hertz, right? Hertz, not megahertz, not gigahertz, hertz, and wavelength, which is in meters. Okay, always remember that. Now, what else is there? So as we'll see, there's a variety of different types of antennas, right? Parabolic, okay, parabolic antennas. Okay, have the following gain, right? Shucks, sorry folks. Oh, okay, yeah, it's equal to this. Parabolic antennas have this gain, okay? This is in linear domain, okay? So heads up. That is equal to 4 pi over lambda squared. Okay, so far so good. Mu sorry, just this equation is not ringing a bell. Just want to bring this up. There we go. Yeah. Okay. So there's a silly thing here. There's something here, like, so, okay. So there's something called effective area, all right? So what you want to do is, just hold on, folks. I just want to make sure this is good. Yeah, okay. So there's something called the effective area. I'll explain. So this is effective area. And again, I'll explain what the heck that means. So effective area is the area of your antenna that your wireless signal ultimately gets received by, right? So it's like some sort of surface, and so it is the area of your antenna that effectively collects all that electromagnetic energy that either gets sent out over a medium or gets intercepted or received over a respective media. So for a parabolic antenna specifically, this is going to be equal to, according to table 8-4. So this is actually a super invaluable table, right? But according to that, so the parabolic antenna, AE, is equal to 0.56 A, and A is pi d squared. So how so? Well, like what does this represent? Let me draw it. So parabolic antenna, or the dish antenna that we see for things like, satellite TV. So what ends up happening is your signal, let's say this is your electromagnetic energy, it's coming that way, right? Gets collected by this dish, okay, and then gets focused to some sort of receiver that, like, so it focuses that energy and is like to some focal point, and then at that focal point there's some sort of receiver, and that goes to whatever your TV set is and such. The effective area is actually the entrance. It's like, imagine this circle, okay, that's at the mouth, if you will, the top. If you were to put a piece of paper across that dish, the area of the paper that kind of follows the silhouette of the edge of that dish, that is the effective area, right? So the D, the diameter, is the diameter across the top, the mouth, if you will, of that dish, right? I think it's R, silly me. Not thinking this morning. Silly Wyglinski. Yeah. Yeah. Sorry about that. Yeah. So yeah, no, it's R. Pi R squared. So sorry. So that's this. Just want to make sure. All right. So this is actually super important. So let me highlight that. So this always, yes. This expression here is generic for everything, right? For all antennas. But for parabolic, which you see a lot of, it has a specific gain, and it's specified by that. And that is the area of the mouth, if you will, of your dish, your parabolic antenna. This gives you the effective area, okay? And then that's what gets plugged into here to AE. Now, there's one more, okay? This is very, very, very important, okay? And this is the free space gain, or free space loss, okay? And it is equal to, so lambda, wavelength's important, pi d squared all squared, right? And L, okay, some loss, incidental. Okay. So, okay. So incidental is if we start off transmitting and already we had a loss at the transmitter, that's what it means by, like, straight out of the antenna, like even before the antenna, like this is the loss that's incurred or gain of the transmit antenna, sorry, of the transmitter system. This is what it is, okay? So what happens is, what this guy does is, this is a free space path loss, right? So we got free space path loss. We got the parabolic antenna gain, and very importantly, the relationship between frequency and wavelength. And some people will talk about the free space path loss in terms of the from end to end. You might say, well, what is this in relationship to? Well, if you look at it, it's kind of like the volume, or sorry, the surface area of a sphere. So let's actually see what is the expression for surface area. And you might, why is Wyglinski looking for surface area of sphere? First of all, I need to learn how to spell sphere. Yeah, way to go, Wyglinski. Okay, so very, very important. So surface area of a sphere, what is it equal to? Let me go to the next slide. This is what it's equal to. So according to Google, because it does not lie, the surface area of a sphere is equal to this. All right, so that's cool. So you might say, okay, so what? Well, okay, so hold that thought. So first of all, so we have this sphere. Our antenna is centered, transmit antenna is centered at the bottom of it, at the center of it. Okay, radius. Okay, so we have some sort of radius. Okay, cool beans. So it has a radius. So now the surface area is effectively this entire thing surrounding it. All right. Now, so now what we're interested in is a relationship between the voltage and the power, and that's a squared relationship. So again, I don't want to go too much into the physics, but the way to understand what the heck is happening here, why do we have, okay, so when we propagate a signal from point A to point B, what is going on? So let's say here's my transmit. I'm gonna do something called a point source. So this is like super ideal. So what this does effectively is it emanates spheres of energy. It's equally radiating energy all over the place. In a minute, I'll explain how this is not happening whenever you have an antenna. But for now, let's assume that this thing is creating beautiful spheres of energy that are emanating upwards, right? Okay, so let's say my point source produces a signal, right? So, and assume the energy produced, the energy produced by the point source is uniformly distributed, that's why it's a point source, across the entire surface of that sphere. So, and then it begins emanating outwards with increasing radius. What's happening? Well, assuming that this energy is uniformly distributed across the surface of that sphere, what's the density of the energy across the surface of that sphere? It's decreasing. It's decreasing as a function of R, okay? And what do we know about the relationship of R with respect to the surface area? Well, it's this, right? So as R begins to get larger and larger and larger and larger, the density of that energy, right, begins to decrease quite significantly. So what happens is, so a couple of things to note. So first of all, the energy, okay, that's produced by the point source, okay, is uniformly distributed across surface of sphere, right? The other thing, very important, is that energy is always conserved. We don't have magically the total energy contained within that sphere becoming less or becoming more. It's always a constant. That's physics there, right? So the energy is always there, but the energy is getting constantly redistributed across that sphere. So as soon as it hits this receiver, right? Oh boy. You know what? I'm going to read all of it. That's like an awful, that was awful. Let me draw it. That's much better so far. Wow. Yeah, that's it. Good enough. So what ends up happening, your receiver, when it picks up that emitted signal, remember I was talking about effective area? Let's do a close-up. Okay, next slide. Here's your receiver, or the antenna, or whatever the receiver, right? Whatever area it picks up from the transmitter. Shucks. Let me try again. Okay. Now, whatever area it picks up. So, like, let's say if we even zoom in more. Like, so, okay, that's the receiver. Now, this is not a point. Well, we don't have point receivers, right? Because if it's infinitesimally small, it's not effectively, it's not going to pick up energy. So let's say this point receiver actually is like, it doesn't make sense because it won't pick up any energy. So let's say it picks up like some sort of antenna, right? So it has some sort of surface area. It's collecting. So let's say that's the energy on the sphere's surface. It's collecting only that much. So when I was talking about effective area, I'm effectively referring to something like that. That is the area that I'm collecting, okay, EM energy from TX. That's what I'm talking about, okay? And so path loss, what it's representing is the physics, right? The physics of having energy, okay, decreasing as a function of distance from the source due to this relationship of, like, first of all, conservation of energy, but secondly, very importantly, so the energy has to be conserved, and you have this like sort of like a magical sphere that the energy is being distributed on the inside of that surface area, and that your antenna is only picking up a small portion of that energy. Now, as an aside, this is actually kind of kooky, and this has been around for like for a century, effectively. What happens is, in the old days, you know, you had well, did you have FM? Definitely AM radio, and you had other radio stations, like radio stations. What people would do, okay, this would be kind of a cool MQP project, is that they would have in their backyard, hey, I need electricity or something like that. Ooh, that. So don't do this. This is actually really bad news. What people effectively did is they put out antennas. They put long strings of metal, right? And what they would do is they would use this to collect electromagnetic energy, okay, from wireless signals to power stuff. Okay, so they basically did something. They did some sort of energy harvesting. Now, there's a there is a reason why this is kind of like somewhat illegal. Well, no, it is because from regulatory standpoint, this is why. So let's go back to our friend the sphere, right? So suppose here's your point, and it's emanating from there, right? Mew, 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 mew. And then you have your antenna here, and you use it just to energy harvest, right? And let's say you use a really big antenna. What are you doing? Well, what happens when the sphere grows even more, right? Well, what happens is you're now collecting, you're actually, remember about the conservation of energy? If I now take, the only way I can incur a loss, right, to the overall energy is if I take energy actively out of that sphere. And that's what I'm doing with something like an energy harvesting type of device. So that's bad news. Like, well, what I'm effectively doing is I'm decreasing energy from that sphere, which means I'm weakening that signal even further beyond whatever R as it's increasing, which means I'm denying, let's say, signal, like let's say I have another transmit antenna over here from collecting, or I make the signal it intercept much weaker than the theoretical, right? So let's say that's R1 and that's R2, and I have an energy harvesting antenna here. That's kind of bad news, because then I'm weakening, I'm taking out energy from that overall sphere, and I'm making that receiver its received strength, signal strength, much weaker than it should be. Okay, so that's why that's kind of bad news. So okay, so I really digress, but I think I really want to emphasize where this comes from, and that's why I want to look at, and I took a little bit of time and I was a little bit befuddled, this guy. Where did that come from? That, okay, if you look at it, okay, and the D is the diameter, but what you do is this could be equal to, right? So lambda over 2 is actually kind of important. You see this all over the place in antenna design. That's kind of a nice number. We use it a lot of cases, like for instance, if we have multiple antennas and we want to space them out, there are really a lot of great physical properties with respect to having things half wavelength apart, right? Or half wavelength in terms of design. So in particular, again, remember electromagnetic energy, okay? So if you have an antenna and you have energy hitting it, I want to convert that into electrical energy, because that's what an antenna does. An antenna, a receive antenna or transmit antenna, is the conversion between, let's say, a wired medium, in this case the antenna, with a like unguided medium like the air, right? So half wavelength, like for instance, if you have a piece of metal that's lambda over 2, is great, because remember, we deal with sinusoids and cosinusoids. Half wavelength is what? Half a period, right? Here's a wavelength, right? Sorry, no, yeah. Half a period of the sine or cosine wave, not a symbol period, okay? Very important. This is not TS. So what we got is this or this. Of course, we can have multiples of half wavelengths. So we could, like on this antenna, we could also have things like this. Okay, we could have this, right? We could also have, we have multiples, all right? But usually what we want is at least lambda over 2 or multiples thereof. That is exciting, that antenna, because then that allows for, because of things like Faraday's law, we can convert that into electrical energy on the wired medium, which is the antenna. And then that carries the modulated signal that goes to our receiver that gets decoded ultimately into a digital format. All right. Okay, so that's a lot of physics there. And again, this is from like the electrical and computer engineering standpoint, right? It's probably super over idealized, and people, even in like, you know, let's say engineering folks that specialize in RF frequency front ends or physics, right, are looking and saying, that guy doesn't know what he's talking about. But at least this kind of is like, you know, from my standpoint, more of the wireless communication system engineering type of person, this is how I kind of see and understand the world. And there's a heck of a lot of assumptions and idealizations here. So ultimately, what I want to do is this expression here accounts for my receive antenna getting a sliver of the transmit power from the transmit antenna. Now, again, you might say, well, again, like what's the difference between antennas? And that ties into the sphere as well, right? So parabolic antenna had this. So in reality, there's no such thing as a point source. We don't have the all-powerful single point source that effectively irradiates energy uniformly everywhere in space. Doesn't happen, right? We don't have such a thing. We have things like parabolic antennas. And where the opening here, and we talked about that, that's the effective area, collects that energy as it propagates from the point source, right? One thing to keep in mind, at very, very large distances between transmitter and receiver, this, you know, the spherical area, as it propagates away from the point source, the surface that you intercept can be approximated as a flat surface. If you're close to it, it'll look round, but far away it's flat. So that's how we can pull off something like, assume just the surface area there, okay? But we also have others. We have, like, for instance, dipole antennas, okay, dipole. And these are simply like a line, literally a wire, right? In this case, it could be like lambda over 2 or a multiple of, and a dipole antenna, like, you know, feeds into your system, right, and translates the wireless energy into electrical signal, right? So in addition to that, oh yes, my favorite, there's also things like horn antennas, okay? So horn antenna is kind of a cool thing, especially if you, at higher frequencies, but what horn antenna is, looks like this, looks like a horn, okay? Yeah, like that. And then what happens is at the back, you have some sort of conversion, okay? So what you'll have is you have a wired feed, okay? And that will feed into, oh shucks. Well, what effectively this becomes is some sort of waveguide. And what it will do is, at the back, there's some sort of feed, okay? And what that feed does is it converts the electrical energy on the wire to some sort of electromagnetic, like wireless signal, and then it propagates outwards. And as it propagates outward, this horn essentially is like if I put my hands over my mouth, if let's suppose it's a point source. Well, first of all, I'm making it highly directional. It's going to go out this way. And I'm also amplifying it, okay? So this shape also amplifies that signal outwards, okay? So that's a horn. So there's a variety of different variety of different types of antennas that pull this off, okay? There's more, but again, like if you take a course, like an antennas course, there's going to be a lot more information on how that works. So, okay, so antennas. So what effectively happens is, like, let's look at a use case. Like for instance, so suppose you have a parabolic antenna. Okay, let's suppose this is at the transmitter. That's at the receiver. Suppose they're separated by some distance, okay, in meters. All right, and the question would be, like, what would be the ratio? So this is important. So what would be the ratio between the transmit power and the receive power? Like, let's suppose I'm not given a value for either, but I just want to know what the ratio is. I'm given these physical characteristics. Suppose I also know that what the radius is here, the transmitter, and I know what the radius is up there, okay, at the receiver. I think I pretty much have all the information I need to pull this off, right? Yes, I do. So the way to calculate this, of course, there's also, like, let's say there's any particular losses or gains at either a transmitter or receiver, but what the way this translates into is what's the end-to-end gain or loss? The way it's calculated is it is going to be the gain or loss of the antenna, transmit antenna, the gain or loss of the receive antenna, and the path loss, the free space path loss. And that's what this is equal to. Okay. So what does this, so if you look at this, what it will look like is something like this. Shucks, sorry. Messed up the equation. But it's actually pretty important. They boop, boop, boop. Receive over transmit. Very, very important. Otherwise, you will have like the inverse gain. So this is going to be equal to, it's going to be equal to whatever the gain is. And we saw what that is for a parabolic antenna. And the free space path loss, what's that? That's going to be equal to lambda, again, 4 pi d, the diameter, right, squared, GAR. Now, recall what these are. Well, these are going to be for parabolic antenna. Pi, and then the effective area is going to be 0.56, and then, yep, and then same thing here. I could choose different dish sizes, okay. So, and then, okay, now, so that's what this comes out to. So if you get a question like this, and then as an aside, if I give you frequency, let's say this is operating a carrier frequency, because remember, this is all based off of the carrier frequency. You'll need to convert everything to lambda. So don't say, oh my God, how do I convert this to lambda? This is the conversion, and 3 times 10 to the 8 meters per second. Remember that. I think that's the only sort of constant, physical constant I can remember. Like seriously, I have a really bad memory of constants, but this is the only one I remember. If I ask you to do this in dB, what is multiplication in the logarithmic domain? Lo and behold, what this is going to be equal to in terms of dB, okay, is going to be equal to, so let's say 10 log 10. This ratio is equal to this guy in dB plus like this guy squared dB So, shucks. What this means here is that you just have to take the 10 log 10 of it plus this. AR and DB. So you just have to take 10 log 10. Now, you can go even more crazy. Like, okay, so first of all, what happens with an exponential? Well, now that becomes a product. And if you divide something, it's minus. And if you multiply something, it's plus. So you could stretch this out and you can put everything in the decimal value. So for instance, if I give you a class test question, I say, well, I want this answer in dB. Here are the gain terms. Usually when we refer to gains, those are already in dB. So I'll say, well, here's the gains in dB. Doesn't make sense to convert them into linear, only to convert them back into logarithmic, right? But you're going to have to do the rest of these things. So what this would look like is, so let's say we do it like, 10 log 10. Okay, and then we would have 10 log 10 gain term, right? And that's usually quoted, and then let's say 10 log 10. So the transmit and receive antenna gains, that's something that's within our control. As engineers, we can design that. Now, here's the other stuff. Shucks, yes. So it's going to be 2 because it was squared, right? And now what do we have? So we have, so first of all, it's 10. So it's going to be 10 log. So what do we do? I don't know. Yeah, so what we want to do, 10 log 10. So what is it again? So it's going to be lambda over 4 pi d squared, correct? So like if we break this thing down, what do we have? So if it's just logarithmic scale, first of all, this guy now becomes 2, and then it's going to be, shucks. So yeah, we do, if we just take the log of this, forget about this, like for now, what it would be is like log 10 lambda minus, okay, and then it would be log 10, okay, and then what we would have this multiplied by 10, so this would be all 20, and then you just work this out. So that's, yeah, so then we would apply that, so this would actually be 20, all this, and this would give us our answer in dB, which is usually whenever we talk about end-to-end, we usually refer to it in decibels anyway. Now, before I call it a day, all right, there's a few other terms. So like, first of all, there's decibels, dBm, and there's also dBi, right? This is decibel, milliwatt, milliwatt. Okay, and this is decibel isotropic. So isotropic. So what this refers to, so remember that decibels is unitless. Decibels, unitless. It's a ratio. It's always done with respect to the magnitude of a ratio, right? So whenever we have this PRX to PTX, that's great because the units cancel out and we take the dB of that, right? 10 log 10. What happens if we don't have such a thing? Well, then what we do is we sometimes take the ratio against 1 milliwatt. Decibel isotropic is interesting because what that does is, so I mentioned about like the point charge, right? And point source and how it's all over the place. What happens if we just look at the XY plane and the energy? So we have this. So let's say this is my transmitter and it's sending out energy in all directions, but not in the vertical. Like, let's forget about like we only want to concentrate energy being propagated in the XY plane, because let's say here I am and I want to pick up a wireless signal. Here's my friend, he wants to pick up a wireless signal. Here's my wife, She wants to pick up the wireless signal. And we're all in the XY plane. We're not above or below it. We're two-dimensional. And then I have another type of transmit antenna that only propagates like this. And it has, let's say, energy like that. What I would like to know is the ratio between, let's say, the transmit power in this, with this antenna, this special antenna, against isotropic. I would do something like decibel, I would do something like dBi, right? So then I would use that value, not just dB, I would do dBi to show kind of like in this case, the gain of using this specialized antenna over isotropic, which has like unity gain across all 360 degrees in the XY plane. All right. Oh boy. So that's a lot of stuff I covered, folks. So yeah, sorry about that. I'm going to try and wrap up, but I think the slides pretty much summarize everything I just talked about. Like, okay. Oh yeah. I'll talk about that next class. But yeah. Hey, I pretty much, there you go. Yep. So basically, all of this all of this summarized what I just talked about over the last hour. So yeah, so lecture slides are great. Definitely use them as a reference, but really any sort of link budget analysis question that I will send your way for this course will really kind of focus on this concept. So you have your transmitter. What is the gain of the transmit antenna? Plus, if there's any sort of RF hardware that amplifies the signal before it gets sent over the propagation medium will have a gain, but it's really a loss. The power is going to definitely decrease as a function of distance to a receiver, which it will have a receive antenna that hopefully will increase the strength of the signal. And then it gets converted, then it's like analog to digital converted, right? So you really need to be that end-to-end, that ratio, PRX over PTX, super critical. You really need to know how that works. So that concludes lecture 27. I know that's kind of a long slog of a lecture, but you will be using this in the wireless domain continuously. If you have a transmitter or receiver and you're trying to figure out, is this making sense? Like seriously, even now I have a research project and we just set up a transmit receive link. And it's like, do we know if it works? We look at the data sheet for the transmit antenna, the data sheet for the receive antenna. What is the radio capable in terms of transmit power? And then we use some sort of instrumentation to collect what the receive power is. And we say, are we golden or is something wrong? And theoretically, like these equations are pretty good. They capture the physics of the world, of the reality around us pretty well. So if something's off, especially if it's like 30 dB off, there's something that requires additional digging around to make sure that like there's something not quite resonating well. All right, folks. So that concludes lecture 27 of ECE 3311. I know I covered a lot of stuff. Your textbook goes into kind of like a similar discussion. If you love this topic and stuff, there's actually a lot of other courses out there that are just like exclusively on the electromagnetic characteristics of things like the free space path loss and antenna design and the electromagnetic sort of properties of the radio frequency front ends at the transmitter and receiver. But at least this kind of gives you some useful tools on how to at least approximate what is the impact of these components of your communication system on your transmitted and then receive antenna. So with that, that is lecture 27.